Okay, this is 3rd of March 2025. I am back to this. So today's first topic is exploring the regular submanifolds conditions and studying critical points and regular values. There are some important theorems that characterize submanifolds. So let's begin with the definition. If f m to n is a smooth map between smooth manifolds, then what we have is a point P in M is called a critical point if f star P from Tm to Tf of P n is not surjective. Okay. Okay. Point P in M is called critical point if the push forward or differential of f is not surjective, and point Q in N is called a critical value if f inverse of Q has a critical point. Otherwise, Q is called a regular value. Let's just see what Sard's theorem is. So it seems to mention whether is also Sard's lemma or Marshall lemma is a result in mathematics that has a set of critical values, that is the immediate set of a smooth function f from one equal space and mindful to another. Then null set that it has Lebesgue measure 0. Oh, I see. I see. So we have a quick remark that Q in N is a regular value if either f inverse Q is empty or for all P in f inverse of Q f star P is surjective. Yeah, I mean it has no critical points. Matlab, it has no critical points, so all points are regular. Matlab, it is surjective. So f star is defined for all points and for all TFPN. Note that if m is less than n, if dim m is less than dim n, dim m is less than n, then dim m is greater than n, then all points of n are regular. Yep. Since it's a map, it has to map to all of n. If n is greater than n, then if m is greater than n, then it can go to the machine and check one thing. Yep, so I'll briefly mention about Sartre's theorem here. It's probably good to note it. Right, what was Sartre's theorem again? So currently the Sartre's theorem asserts that the critical value set of critical values set measure 0. Let's start with examples. Let f to r be a smooth path. Then note that P in M is a critical value, the critical point of f if and only if f star is 0. It follows from I mean a one-dimensional vector space, some n-dimensional vector space to one-dimensional vector space is not surjective only if star is 0, I guess. Because any non-zero element, once you map it, it just becomes a surjection. Yeah. One can also see this by considering the Jacobian of this, the local form of this Jacobian Rn to Rn, R into R, which is f of I inverse, right? The Jacobian of this has to be 0 because just revisit this argument in 2's book. Yep, exactly. Yeah. Cool. So next example we have F from M set of n cross n matrices, from set of n cross n matrices to symmetric n cross n matrices. Interesting. On that, F inverse of I equals to O(n), set of all orthogonal matrices. So what we want is error surjection, right? Right. So if it's a surjection, then the rank has to be greater of m comma n or less what? Okay, let's see. Yeah, there's a good argument about this, about the rank of the matrix and injection and submersion and immersion. Yeah. So it's good to look at these things. Let me just open tools again. So submersion, yeah, see. So F star P is surjective if and only if dimension of m is greater than n for our case, and the rank of the Jacobian of F, local Jacobian, F locally, it's called Jacobian, is precisely the lesser of these m comma n, which is n not this. So that you can just confirm by that. Okay. Yeah. Now we'll come to exact this thing. One has to study a bit of linear algebra, of course. Yeah, from linear algebra we basically have a linear map is surjective if and only if it's of maximal rank, right? And injective also the same case, maximal rank, and then yeah, cool. So also from matrices. Now what we want to find is we want to find the rank of f star at all points in On and see if if f inverse I has any critical points, right? So suppose A is in On, then what is the rank of f star dA m n r to di sm n r. Note also that injective inverse why did we consider specifically C in SMNR? We have to consider any element in TI SMNR, and is this our claim that any C belongs to SMNR is actually in TI SMNR? Yeah, since SMNR is basically diffeomorphic to Rn times n plus 1 and into n plus 1 by 2, then the tangent space is the same thing, Rn to n plus 1 by 2. I think it follows that tangent vectors at an entity of SMNR are also SMNR. So yeah. Yeah, that is cool. Yep, it's exactly that. Yeah. So a star projection for all A and F inverse of I. So I is a regular value of F. Now we have a very interesting theorem. Theorem is that it's the regular level set or regular value theorem if F from N to M is a smooth man and C in M is a regular value of F, then F inverse of C is a regular submanifold of N. What the fuck? C is a regular manifold. The regular submanifold of N of dimension M minus M. We'll just say codimension of okay. So clearly for all F inverse C, a star is surjection, so N is greater than M, dim N, and is a regular submanifold of N, so N minus M, which is basically the codimension of N. Of codimension M, I would prefer to write it as of codimension M. Interesting. we'll prove it. Before proving it, we'll just do an example. Yeah, proof is simple actually. I mean, it's interesting. Before proving, we can show something immediately. To show immediately from last example that ON consider F equals to det from NR to R. Consider F equals to det NR to R. Then R basically F inverse of 1, right? To show one is a regular value, the regular value of F, we consider, we write if A is a critical you really need to start using the BW DB DBI is a critical point of F, then that of J equals 0 for all I, comma j. Implies that I think it's important for us to understand why is it true. So for the rest of this session, we'll be basically proving this fact that indeed inverse the regular value. If C is a regular value of a smooth map F between manifolds, then F inverse C is actually a regular submanifold. Let's see how this can be done. Let's parse through the things and see intuitively why this is true. Okay, I mean, yeah. Yeah. Cool. So let's start with the proof. For that, let's take the image. So we're back to the setup. Let's pause. Okay, so for P in F inverse for P in F inverse of C, choose a chart U comma phi centered at P. Okay, choose and the chart V comma psi containing C centered at C, and psi of C equals 0. Good. Assume F of U is inside V. Acha. You just take a subset of it. So psi circ F circ phi inverse of 0 is equals to 0. So 0 is marked as 0 by F locally. Okay. Can you, okay, so can you really assume that F of U is in V? P belongs to F inverse C. You have a neighborhood around C. You have a neighborhood around P. Okay, so F is a smooth map, so okay, F is a smooth map, then we'll definitely have a neighborhood around P. Basically F inverse V is a neighborhood, then F inverse, yeah. And this precisely comes in, yeah, so, yep. Further, F star Tpn to T Cm is surjective, so the rank of J psi circ F phi inverse is M, smaller one. Yeah. That means, this means J psi F phi inverse can be written as cross n minus m matrix, and B is an invertible n cross n matrix m cross n, sorry, because there exists a rank m. The rank this means J5 inverse can be written as U where A is an m cross n minus m matrix. Matrix. That is cool. Yeah, we can just rearrange the columns. You can surely write it as first also, but consider now theta from U to Rn such that theta of Q equals to phi 1 of Q phi n minus 1 m phi n minus m of Q. Okay, phi, remember, is a chart of n, so use the chart of n. I suppose that is there. Use in n. So it goes to Rn, and now we are restricting m is the smaller one, remember, and you are restricting to n minus m first coordinates, and then what you're saying is that it is psi circ, then the rest of the m coordinates you're using of Q psi f m of Q. What we get by doing this is that precisely get a neighborhood. So okay, theta is from U to Rn. Okay, with the following thing. What you want to do is that shows that F inverse of C is a regular submanifold. So you have to give adapted charts on F inverse C on N that can actually make this happen. So apparently use an adapted chart. Okay, with the chart. This will be our candidate for the adapted chart. Candidate chart for we indeed consider, so yeah, so thing is, once you define this, and you can phi inverse, you can map it from phi of u to Rn, right? Then what happens is, if u Rn to Rn map, it's an Rn to Rn map, then it is invertible, because remember that, yeah, because remember, okay, if it's invertible, there exists an open neighborhood phi of u such that theta of phi inverse of w is open, right? Precisely. Okay, so the thing is, all of these map to C. You open up into phi of u. Okay. W containing 0 in phi of u such that theta of phi inverse of w is open, and then theta of phi inverse of w to theta of phi inverse of w. From w to image is a diffeomorphism. Then consider phi inverse w on subset of u. This is an adapted chart. Okay. This is not yet an adapted chart, but okay. The chart for f inverse C around P, then theta u naught to u, the chart of n, and if Q belongs to f inverse C, it is so if Q inverse, exactly. Perfect. So this will give us the adapted charts, the following. So consider now then theta composed with phi inverse from phi of u to Rn, which is an Rn to Rn map. This takes theta x to first coordinates are basically the same ones, they are just taking phi, so first coordinates are same, it is fine. First n minus m coordinates, but then what you're doing is psi of precisely the m coordinates of that. Psi basically we'll write it as psi circ f circ phi inverse. as an invertible has a Jacobian as the following Jacobian. Equals to B is invertible since B is invertible. Phi O F. Okay, psi F and F inverse. Once you get to that function, the derivative is again by A comma B. Yep, that was nice. So there exists W open in phi of u open containing d0 such that theta sub phi inverse of W is open and theta sub phi inverse from W to theta sub phi inverse of W is a diffeomorphism. Then consider u0 equals to phi inverse of W, which is subset of u. Then is that u0 comma theta is an adapted chart for f inverse of c around P. Since for Q in 0 cap F inverse of C theta of Q theta of Q equals to minus m comma perfect. So basically what is happening is you have a W whatever. Main picture is this N M considered a V C, there's a P, there's a U, phi 0, psi 0. Now this has a rank M, so matlab a minor of rank M, a minor of M, and because M minor is invertible, M matrix is invertible. So what we did was we were able to define a map from using theta. We go to theta such that this can actually go to Rn, where so we considered this map and we saw that it is the transition function between these two are actually is actually diffeomorphism for a neighborhood around what we saw was this, yeah, there is a diffeomorphism between these two, and since there is a diffeomorphism between these two, there is a diffeomorphism between these two, and precisely when you there's a chart, there's an adapted chart here. So there's a chart that goes to actually this when U intersection P was 0. That's what we showed. I think this is worth drawing it out. Yeah. M and phi psi F P U C V theta 0. Okay, so that there's a neighborhood in this, and then there's a neighborhood in this. It almost completes. Yeah, that completes the proof, and that completes theorem map to chart and inverse intersection. Okay, map to chart inverse. Then let's consider. Okay, we should check this for. So it will be a good exercise to check this for. Usually check for Sn to show Sn. Yeah, Sn as a submanifold of R n plus 1. That will be a good exercise. We'll get the adaptive charts and everything. We'll do that sometime, but what we have now is another theorem which we won't prove, but follows similarly. Is called the transversality theorem. It states that if f m to n is a smooth map and P is a submanifold of n, is a submanifold then F is called transverse to P if for all C in P and all Q in F inverse C we have F star of TQM plus TCP equals to TCN. I see. So TCN is precisely F inverse का set plus TCP. Okay. What it's essentially saying is if is okay. So the theorem is that if this holds, then F inverse of P is a submanifold of M. So not only a set, not only a first thing is this should say that all the points all points is sort of a sort of criticality. It should speak regularity, right? In some sense, I think it follows from the above, but you can also prove, I think. You see, you're already saying P is submanifold of N, so you have adaptive charts of P. Now TCN minus TCP, so F star is a projection from TCN minus TCP. Let's see. You can think about it.